long time no see. Well, it's been over a month. I said I'd put a video out the week after and cut away the editing and just show the casting. Well, how about it? I'll show you the casting now. And then also for the rest of the video, we'll look at machining the V-twin, as I pretty much almost have it finished. But before we get into it, I'll show you the patterns for the V4, because I'm sure that is on the tip of everyone's tongue. Where's the V4? I'm just here for the 2 strokes. Yeah, cool, man. So where is the V4? It's here. Well, the pattern's here, and it's still foam, rough as guts, unfinished, needs a lot of attention. So I'll talk about that in a sec. Yeah, so at the moment my full attention is on the V-twin. I've made two sets of those patterns, and shortly after that's finished I'll get to casting those, but that needs 100% of my undivided attention, as casting those is kind of a big deal, not something you can really half-ass. What I've been up to, I cast the other half of the engine. I've done almost all of the machining on the V-twin, so it's almost, I wouldn't say ready to run, but the case halves are bolted together, all the bearing bores are done, the faces are machined for the cylinders. So let's take a look at what I've been doing over the last month. So what you're going to see here is I'll be sieving in some of the sand around the pattern. Now the reason I do this is because I reuse my sand, and after a few of these processes it gets a little bit chunky and doesn't flow so well, so re-sieving it just allows it to better vibrate into all the nooks and crannies. Now, on a side note, what's kind of funny is that the majority of this engine is made of reconstituted Tesla Model 3 wheel rim. So that's just a funny, ironic note, as this engine, internal combustion, was born from Tesla parts.
So I've just faced the left-hand side case using my Chinese 50mm face mill with these aluminium inserts. It's given a fairly nice finish. The finishing pass was 0.1mm deep at a feed rate of 500 millimeters per minute, and the spindle was spinning at 1500 revolutions per minute. Obviously not the best clamp down, as that face there is unmachined, but it's pretty flat. But now I have a reference, I can flip it over and we can machine the other side. So for all of this, I've actually just been using the manual data entry. So just type your code in here and it follows it. So I've never actually bothered learning G-code. I've just used Fusion for everything, but I've sort of taken an interest in sort of programming simple things at the machine, you know, drilling cycles and whatnot, because there's not really any point running a program just to face this part when all I'm doing is going down 0.1 across 45, 300, 45, 300, 45, 300, and so on. So this is a good little learning project for me. So as you can see, this side's come out pretty good. When I clamped it down, I made sure it wasn't too tight because I didn't want to induce a bow into the material. But front to back, it doesn't really have anything. I think corner to corner there's a tiny bit of a rock, although if I clamp it in these two spots, I should be able to face this, flip it, and then I could face it one more time, or I can just run it down on a surface plate. I'll figure that out after. So what we're going to do is clamp this down. And that was opened up, so. So now what we have to do from here is drill some holes at some specific coordinates, but obviously before I do that, this needs to be dialed in. These 4 holes need to be drilled, and I want to bore this concentric to this, the PCD of these holes, so I can make a fixture plate, so I can hold this the other way up in the vise by a plate bolted to these 4 holes. So we'll see how that goes. So seeing as it's a rough casting, here's the plan. I've got this, and it's just a tapered plug. It's 3/4 inches on that end, and I'll place it in here like so in the spindle, and then I'll get a square along here, because this is as cast. Obviously I'm going to have to cut my reference surfaces the first time I start machining. Now we've got to pick a cutter to put that reference face on the bottom. Now that would be nice, but it's, what's the word for it? Leaves a very rough finish, that roughing cutter. So we'll go with the trusty old 8mm. This is the same one that machined all the foam patterns for the V4 and for the V-twin. Although obviously I'm going to reduce this stick out. This was just to clear the foam. Pretty nerve-wracking. I'm just about to run my first ever handwritten G-code. I've tested it in the air a few times, so let's see what happens. So I'm not going to lie, that went perfectly. All the holes in the right spot. So I'm going to run this again, except now I'm going to use the correct size drill bit to tap these holes. M8 by 1.25. .8 mils is the drill size for a M8 by 125, and we're getting about 6.78 was the highest measurement I got. I'll do it again. Get in the hole a little bit. I'll lock it off so you can see. It just came down as I took it out, but we ended up with 6.78. I bumped it on the way out. So the audio was pretty bad. I'll just tell you what I said. So what I'm doing now is finishing all of the tapped holes by hand. And I was just talking about hopefully my rudimentary T5 heat treatment did something to harden this material. I held it at 200 degrees Celsius for 8 hours. Yeah, hopefully Tesla wheel rims are heat treatable. What you're going to see next is the fixture I use to hold the part. So this fixture is awesome as I can locate the part repeatedly and hold it in a vise. Now the plan from here is to find the center of the bore with the dial indicator mounted, or test indicator mounted in the spindle. So here it is, the final result. It sort of sits on 0 and it moves around a little bit. Oh, avoid the tripod. Creeps out by about 0.02. My shoddy camera work. Yeah, it sort of creeps out by about that much at the most, but more or less pretty good. And this has to be finished to size anyway, so these dowel holes will be done at the same time as this, and this will be interpolated and then bored. No, yeah. Between 9.95 and 9.97. So I was going to run a spring pass, but because I'm making these dowels, I'll just make them in the lathe and they'll fit this hole nice. So this one is a through dowel, and then that one's just a solid dowel out in the corner. Awesome. And now all I have to do is go to 0, rewind the program, and I can run it again after adjusting the boring head. So now I need to take a measurement. There they are. And how big's that hole? Interesting, eh? Terrible with imperial measurements. 1 1/4. What's that? 30. Yeah, this is us. We'll go with the higher measurement, 2.9. So we have a through bore here, and this bore here for the OD of this bearing. This was done by facing both faces flat, and then coming up with some handwritten G-code. Now, I've never handwritten G-code before. Fusion 360's CAM has taken care of everything, and I decided, why not give it a crack? So what I did was just handwrote G-code to face all of these parts. Pretty easy, really. It's just dropping it down in Z and then X and Y coordinates. So once both halves were faced,
I started off by machining this face. This is for the PTO, or yes, essentially the important dimensions. This is a standardized size. You may or may not recognize it. I'm not really going to talk about what it's for, but yep, this is a standardized size. So I made this, drilled and tapped these holes M8, and this was all hand programmed, which was pretty cool. So I did a, G81 canned cycle, where I just entered the hole coordinates, the drill depth, and it went around. It made programming at the computer fairly quick. I just wrote up some G code in the notepad and then ran it in the air to make sure I didn't drill a hole straight through the part, and then ran the code for real. A bit, worrisome, but once it drilled the first hole fine, I put it to 100% and it just zipped around, drilled the holes. I bored 2 dowels. This is all in one setup. I bored the location of the 2 dowels. One's a through dowel, one's a solid dowel, and then the dowels were handmade in the lathe to be a transition slight interference fit with those bores. But the bores came out on size. They're meant to be 10 millimeters. I think it's about 9.99 to 10.01, so pretty tight, within 20 microns on the bore. And then once that was done, I set this up with the boring head. Now, once I set the machine to 0, 0, being the origin, I locked the table, placed on my boring head. It's actually on the larger side. I should have bought a smaller boring head. Set it down to about 400 RPM to avoid vibration, seeing as the mill is not all that heavy. And then bored through the part, taking a 0.1 millimeter depth of cut and just adjusting out till I hit bang on that interference fit. So with the boring head, I could dial it down to, within 10 microns. That's about as good as I can measure. So yeah, within 10 microns. And so all of the bearings are a 20 micron interference fit. And then over here, you can see the other half on the mill. So yeah, there was heaps of progress made. I should have made the video sooner, but as I've said in the past, these videos do take a lot of time and they massively get in the way of progress. But again, I like sharing this stuff with you guys, so show your appreciation, give the video a like, subscribe if you actually enjoy this stuff. I'm going to try with this video to make it longer and talk more about what I've actually done, so you can actually learn more about the process and some of the thought that goes into it. So, yep, here's the other case half. Once that side was machined, this was done in the same manner, although it doesn't have that PTO. So the way this was done, it was just finger clamped down to the table, and essentially faced on each side, holes drilled through, dowels done, all in one setup. A few key things when machining a casting is you've got to face both sides. Now your castings aren't going to be completely flat. So what I did to ensure I could get it flat on both sides without clamping flat to the table. So if I'm to explain this, if you put these finger clamps on your part and it's not flat and you clamp it down with a lot of force before facing it, you're going to pull the part down flat, machine the top flat, and then when you take the tension off that bolt, it's going to warp again. So the way around this, or what I do, is I'll have 2 small areas where I'll rest the part on parallels. So ideally, yes, you want 3 points of contact, in a perfect world, instead of 4, so the part's not rocking. So you're only, in my case, I had 2 narrow parallels, sat the part on there, clamped it down central, so it was just resting on those parallels, near enough flat, and then I took some very light cuts with a 50mm face mill. Now, that enabled me to get the entire top surface flat, and then when I released the clamps, the part didn't warp, as I hadn't distorted it prior to machining. And then from there, I could flip it over, machine, put it, down on its face, and then just machine the other side, seeing as I wasn't putting the part into a stress state. So what you're looking at here, I'm using my dowels on the crankcase, and I'm going to place on the already machined half.
So because this is already machined, it means I can indicate the bore, and then I can use that to set my XY0 to bore the other crankcase half. So that will near enough get them almost perfectly mated. Not a bad finish for the roughing end mill. Well, actually it's terrible. It's pretty funny though.